Welcome! Today we'll explore problem number 1027, longest arithmetic subsequence. In this problem, we'll dive into finding the longest subsequence in an array where the difference between consecutive elements remains constant. Let's get started. In this problem, we are tasked with finding the length of the longest arithmetic subsequence in an array of integers, nums. A subsequence is created by selecting elements from the array, possibly deleting some, while maintaining the original order of the remaining elements. An arithmetic subsequence is a special type of subsequence where the difference between any two consecutive elements is constant. For example, in the array 3, 6, 9, 12, the entire array itself is an arithmetic subsequence because the difference between each consecutive pair of elements is 3. The input to this problem will be an integer array nums of size n, and the output should be a single integer representing the length of the longest arithmetic subsequence found in nums. Let's look at the first example for clarity. If the input array is nums equals 3, 6, 9, 12, the output is 4. This is because the entire array forms an arithmetic subsequence, where the difference between consecutive elements is a constant value of 3. Since this subsequence includes all 4 elements of the array, its length is 4, which is the result. Now, consider the second example, where the input is nums equals 9, 4, 7, 2, 10. Here, the output is 3. This is because one of the longest arithmetic subsequences is 4, 7, 10. The difference between consecutive elements in this subsequence is 3, and its length is 3. In the second example, it's worth noting that there are other possible arithmetic subsequences of length 3, such as 9, 7, 10. However, the length of the longest arithmetic subsequence remains the same, which is 3. Moving to the third example, if the input is nums equals 20, 1, 15, 3, 10, 5, 8, the output is 4. Here, one of the longest arithmetic subsequences is 20, 15, 10, 5, where the difference between consecutive elements is -5. The length of this subsequence is 4. This demonstrates that the difference can be negative, and the elements do not have to appear consecutively in the original array for the subsequence to qualify. Now let's take a look at the constraints and edge cases for this problem. The length of the array, nums, is guaranteed to be at least 2 and can go up to 1000. The values in nums range from 0 to 10,000, and the array is not necessarily sorted. The difference for an arithmetic subsequence can be either positive or negative. Considering edge cases, if the array has only 2 elements, the result is always 2, since any 2 elements form a valid arithmetic subsequence. If all elements in the array are equal, the entire array forms an arithmetic subsequence. Additionally, you must handle cases with large differences between elements, such as 1, 10,000, 9999, 2, and arrays where elements appear in random order, like 10, 4, 7, 1, 2. Ensuring your solution handles all these scenarios is crucial for correctness. To tackle the longest arithmetic subsequence problem, let's start by considering 2 main approaches. The first is the brute force approach, which is the most intuitive but also the least efficient. Here, we generate all possible subsequences of the array, check whether each one is arithmetic by ensuring the difference between consecutive elements remains constant, and track the length of the longest valid subsequence. However, since there are 2 to the power of n possible subsequences for an array of length n, and checking each subsequence takes linear time, this method has an exponential time complexity of 2 to the power of n asterisk n. While simple to conceptualize, this approach is computationally impractical for larger inputs. Now, a more efficient method involves dynamic programming with fixed differences. The idea here is to fix a common difference and use a dynamic programming table to systematically track how many elements can form an arithmetic subsequence with that difference. Specifically, the table dp(i)d represents the length of the longest arithmetic subsequence ending at index I with a difference of d. By iterating over all pairs of indices, computing the difference for each pair, and updating the table iteratively, we achieve a time complexity of n squared. This is a significant improvement over brute force. However, the need to maintain a DP table for all possible differences can lead to high memory usage, which is a trade-off to consider. Building on the dynamic programming approach, we can optimize it further by using hashing to reduce memory usage while achieving the same time complexity. Instead of a fixed-size DP table, we use a list of hash maps, where each hash map corresponds to an index in the array and stores the lengths of arithmetic subsequences that end at that index. The keys in the hash map represent differences, while the values represent the corresponding lengths. For each pair of indices, we calculate the difference d and update the hash map for the current index based on the previous index. If the difference already exists in the hash map of the earlier index, we extend the subsequence by incrementing its length. Otherwise, we initialize it to a length of 2, since a minimum of 2 elements is required to form an arithmetic subsequence. This approach maintains the O(n)² time complexity but significantly reduces memory usage by only storing valid differences. The combination of efficient memory management and straightforward logic makes this method highly practical. The key insight here is that we don't need to explicitly store entire subsequences. By focusing on their lengths and differences, we can solve the problem more efficiently. This optimized dynamic programming approach with hashing is chosen because it strikes the best balance between time complexity, space complexity, and implementation simplicity. It runs in O(n)² time, which is efficient enough to handle arrays that meet typical constraint limits on LeetCode. The use of hash maps ensures scalability by keeping memory usage manageable even for larger inputs. Additionally, the implementation is relatively straightforward, avoiding unnecessary overhead while remaining robust and adaptable. Of course, there are trade-offs to consider. Compared to the brute force method, this approach sacrifices simplicity of concept for efficiency. When compared to the fixed difference dynamic programming method, it requires slightly more complex logic to dynamically manage the hash maps, but this is a small price to pay for the reduction in memory usage. Ultimately, this method provides the ideal combination of efficiency and practicality, making it the most effective strategy for solving problem number 1027. In this problem, the goal is to find the longest arithmetic subsequence from a given array. An arithmetic subsequence is a sequence where the difference between consecutive elements is constant. To start, we can explore a brute force approach. First, we generate all possible subsequences of the array. This can be done recursively or using bit masking, ensuring that the relative order of elements is preserved. For example, if the array is 1, 3, 5, the generated subsets would include 1, 3, 5, 1, 3, 1, 5, 3, 5, and 1, 3, 5. Once we have the subsets, the next step is to check whether each one satisfies the arithmetic property by calculating the differences between consecutive elements and verifying that the difference remains constant throughout the subsequence. For instance, consider the subset 1, 3, 5. The differences between consecutive elements are 3, 1 equals 2 and 5, 3 equals 2, which are consistent. This confirms that 1, 3, 5 is an arithmetic subsequence. To track the longest arithmetic subsequence, we introduce a variable called longest_length, initialized to 0. As we iterate through each valid subsequence, we compare its length with the current value of longest_length, updating longest_length whenever we find a longer subsequence. After examining all possible subsets, the value of longest_length will represent the length of the longest arithmetic subsequence, which we then return as the result. Although the brute force approach is straightforward, it has significant limitations. Generating all possible subsets of an array has exponential complexity, as the number of subsets for an array of size n is 2^n. This makes the method highly inefficient for larger inputs, especially for arrays with more than 20 elements. Additionally, many subsequences are checked redundantly, leading to unnecessary computations. To implement the brute force approach, we can use specific data structures. For subset generation, recursion or bit masking can help efficiently represent the inclusion or exclusion of elements in a subset. We can temporarily store generated subsets in a list for validation, while the length of the longest valid arithmetic subsequence is tracked using a variable like longest_length. To improve efficiency, we can avoid generating all subsets and instead focus on pairs of elements, dynamically extending subsequences from these pairs. A more optimal solution involves dynamic programming. Using a hash table, we can store the length of the longest arithmetic subsequence ending at each index for a given difference. This eliminates the need to repeatedly validate subsets. In terms of complexity, the brute force approach has a time complexity of O(2 to the power of n*n), as it involves generating subsets and validating each. The space complexity is 2 to the power of n, due to the storage of subsets. For example, given the input 1, 2, 3, 4, we can demonstrate how this optimization works in practice. Starting with the input 1, 2, 3, 4, we generate all possible subsets, such as 1, 2, 3, 4, 1, 2, 1, 3, 1, 4, 2, 3, 4, 1, 2, 3, and so on. For each subset, we check whether it satisfies the arithmetic property. For example, 1, 2 has a consistent difference of 1, making it valid. Similarly, 1, 3 has a difference of 2, and 1, 2, 3 has consecutive differences of 1, so it is also valid. Among all valid subsequences, the longest one is 1, 2, 3, 4, with a consistent difference of 1 throughout. Thus, the maximum length is 4. While this approach works, it is clear that it becomes inefficient for larger arrays, making optimization necessary for practical use. Here, we start by defining a class called solution and implementing the method longestArithSeqLength. The goal of this method is to find the length of the longest arithmetic subsequence in the given list of numbers, nums. First, we determine the length of the input list, n, and handle the edge case where the list has one or no elements. If n is less than or equal to 1, we simply return n as the result. Next, we initialize a list called dp, where each element is an empty dictionary. This structure will allow us to store the lengths of arithmetic subsequences ending at each index, with keys representing the common differences of these subsequences. We also initialize a variable max_length to 1, which will keep track of the longest subsequence we've found so far. Now, we use a nested loop to iterate through all pairs of indices, j and I, where j is less than I. For each pair, we calculate the common difference diff between the two numbers at these indices. If this difference already exists as a key in dp, j, it means we can extend the corresponding arithmetic subsequence by one more element. In this case, we update dp, I, diff, to be dp, j, diff, plus 1. Otherwise, we start a new arithmetic subsequence of length 2 at index I with the given difference. At each step, we also update max_length to ensure it reflects the longest subsequence seen so far. Finally, after processing all pairs of indices, we return the value of max_length. This variable contains the length of the longest arithmetic subsequence found in the input list. By using dynamic programming and iterating through all possible pairs, we efficiently compute the result while ensuring that each arithmetic subsequence is tracked based on its common difference. This approach ensures that we cover all potential subsequences and achieve the desired solution in optimal time. Here, we start by importing the necessary Java utilities and defining our solution class. The main function, longestArithSeqLength, takes an array of integers as input. The first step is to handle the edge case where the array has one or no elements. In such cases, the length of the longest arithmetic sequence is simply the size of the array. Now, to solve the problem, we use a dynamic programming approach. We define an array of hashmaps called dp, where each hashmap corresponds to an index in the input array. Each hashmap stores key-value pairs where the key is the difference between two numbers and the value is the length of the arithmetic sequence with that difference ending at the current index. We initialize the dp array by setting up a new hashmap for each index in nums. We also initialize a variable, maxLength, to keep track of the longest sequence we find. Next, we use a nested loop to compare each pair of indices. For every pair, we calculate the difference, diff, between the numbers at those indices. If the difference already exists in the hashmap for the earlier index, we use it to extend the sequence. Otherwise, we start a new sequence with a length of 2. The updated length for that difference is then stored in the current index's hashmap, and we update maxLength if this new sequence is the longest one found so far. Finally, after the nested loops have processed all pairs of indices, the maxLength variable contains the length of the longest arithmetic subsequence in the array. We simply return this value as the result. This implementation efficiently tracks all possible arithmetic sequences and their lengths using dynamic programming and hashmaps. By iterating through the array and updating the dp structure, we ensure that the solution is both time and space efficient, making it well suited for larger input arrays. To solve the problem, we use a dynamic programming approach where we track arithmetic subsequences ending at each index. Starting with the first example, nums equals 3, 6, 9, 12, we initialize n to 4, which is the length of the array, and create a DP array with 4 empty dictionaries. Each DP, I, will store the difference of the arithmetic subsequence as a key and its length as the value. We also initialize max_length to 1, as the minimum subsequence length is 1. For the first outer loop where I equals 0, there are no earlier indices j to compare with, so we move forward. For I equals 1, we calculate the difference between nums 1 and nums 0, which is 3. Since this difference is not in DP 0, we start a new sequence of length 2 and update DP 1, 3 to 2. At the same time, we update max_length to 2, as it's the maximum length we've encountered so far. Next, for I equals 2, we calculate differences with previous indices. First, with j equals 0, the difference between nums 2 and nums 0 is 6. This difference is not in DP 0, so we start a new sequence, setting DP 2, 6 to 2. Then, with j equals 1, the difference is 3. Since this difference already exists in DP 1, we extend the existing subsequence by incrementing its length. Thus, DP 2, 3 becomes DP 1, 3 plus 1, which equals 3. We also update max_length to 3. Now, for I equals 3, we again calculate differences with all prior indices. With j equals 0, the difference is 9, and since it's not in DP 0, we start a new sequence, DP 3, 9 equals 2. With j equals 1, the difference is 6, and similarly, we start a new sequence, DP 3, 6 equals 2. Finally, with j equals 2, the difference is 3, which already exists in DP 2. So, we extend this sequence, updating DP 3, 3 to DP 2, 3 plus 1, which equals 4. This updates max_length to 4. After processing all elements of the array, we find that max_length is 4, which is the length of the longest arithmetic subsequence. Now, let's consider example 2, where nums equals 9, 4, 7, 2, 10. We initialize n to 5, DP is an array of 5 empty dictionaries, and max_length is 1. For I equals 1, we compare with j equals 0. The difference between nums 1 and nums 0 is -5. Since this difference is not in DP 0, we start a new sequence of length 2, updating DP 1-5 to 2. We also update max_length to 2, as it's the maximum length encountered so far. For I equals 2, we calculate differences with previous indices. With j equals 0, the difference between nums 2 and nums 0 is -2. As this difference is not in DP 0, we start a new sequence, DP 2-2 equals 2. Then, with j equals 1, the difference is 3. Since it's not in DP 1, we start another new sequence, DP 2, 3 equals 2. Now, for I equals 3, we calculate differences again. With j equals 0, the difference is -7. As it's not in DP 0, we start a new sequence, DP 3-7 equals 2. With j equals 1, the difference is -2, which already exists in DP 1. So, we extend this sequence, updating DP 3-2 to DP 1-2 plus 1, which equals 3. This updates max_length to 3. With j equals 2, the difference is -5, which doesn't exist in DP 2, so we start a new sequence, DP 3-5 equals 2. For I equals 4, we calculate differences with all prior indices. With j equals 0, the difference is 1. Since it's not in DP 0, we start a new sequence, DP 4-1 equals 2. With j equals 1, the difference is 6. This difference is not in DP 1, so we start another new sequence, DP 4-6 equals 2. With j equals 2, the difference is 3, which exists in DP 2. Thus, we extend this sequence, updating DP 4-3 to DP 2-3 plus 1, which equals 3. Finally, with j equals 3, the difference is 8. Since this difference is not in DP 3, we start a new sequence, DP 4-8 equals 2. After processing all elements, max_length remains 3, which is the length of the longest arithmetic subsequence in this example. In the final example, nums equals 20, 1, 15, 3, 10, 5, 8. This example demonstrates how the algorithm handles multiple difference values, such as -19, -5, and -2, among others. The longest arithmetic subsequence in this case is 20, 15, 10, 5, with a common difference of -5. By tracking differences and extending sequences as needed, we find that the maximum length of any arithmetic subsequence in this array is 4. This completes the solution walkthrough for the problem. To analyze the time complexity of our solution, we can break it down into a few components. First, the outer loop runs from I equals 0 to n1, meaning it contributes n iterations. For each iteration of this outer loop, there's an inner loop that iterates from j equals 0 to i1. This inner loop runs up to I times in the worst case for each value of I. When we sum up the iterations across all values of I, we get 1 plus 2 plus 3 plus n1, which simplifies to n asterisk n1/2. This evaluates to n squared. Additionally, within the inner loop, calculating the difference between nums I and nums j is an O1 operation. Similarly, updating the DP table involves setting a value in a dictionary, which also averages to O1. These operations, while constant, are nested inside the loops and don't affect the overall asymptotic complexity of the algorithm. When we combine these components, we see that the nested loops dominate the time complexity. The outer loop contributes n, and the inner loop adds another n, for each iteration of the outer loop. Multiplying these two together gives us a total time complexity of n asterisk n, which simplifies to n squared. Now, shifting our focus to space complexity, we must account for the DP table used to store the results. The DP table is implemented as a list of dictionaries, with one dictionary corresponding to each index of the input array. In the worst-case scenario, each dictionary could store up to n entries if all pairs of indices produce unique differences. Therefore, the total space required for the DP table is proportional to the number of indices multiplied by the maximum number of unique differences per index, resulting in n asterisk n, or n squared, in total. In addition to the DP table, we also consider auxiliary space requirements. These include variables like max_length, loop counters, and the current diff being calculated. Since these are just a fixed number of variables, they contribute O1 space. Consequently, the overall space complexity remains dominated by the DP table storage requirements, which is n squared. Now, let's examine the best, average, and worst-case scenarios. Regardless of the specific input, the algorithm always processes all pairs of indices, j, I, or j less than I, iterating over them in the same manner. This means that both the time and space complexities remain n squared, in all cases. The number of entries in the DP table is entirely determined by the length of the input array, n, and not the specific values within nums. Let's compare this optimized approach with the brute force method to highlight the efficiency gains. In a naive solution, we would generate all subsequences of the input array to check whether each one forms an arithmetic sequence. Since there are 2 n possible subsequences, and verifying each subsequence for the arithmetic property requires up to n operations, the total time complexity of this brute force approach is 2 to the power of n asterisk n. This exponential complexity is infeasible for large values of n. In contrast, our optimized solution uses dynamic programming to incrementally build arithmetic subsequences. By storing intermediate results in the DP table, we avoid redundant calculations and achieve a polynomial time complexity of n squared. This is a dramatic improvement, making the solution far more scalable. To solidify our understanding, let's formally prove the big O bounds for the solution. For time complexity, we know that each pair of indices, j, I, is processed exactly once. The operations performed for each pair, such as calculating the difference and updating the DP table, are O1. Since the total number of pairs, j, I, is n asterisk n1/2, this simplifies to n squared overall. For space complexity, the DP table dominates the analysis. With up to n differences stored for each of the n indices, the table requires n squared space in the worst case. These bounds confirm that both the time and space complexities of the solution are n squared, making the approach efficient and suitable for the problem constraints. One of the most common mistakes when solving this problem is confusing subsequences with subarrays. Remember, subarrays are contiguous, meaning the elements must appear consecutively in the original array, while subsequences can skip elements as long as the order remains unchanged. Misapplying subarray logic often leads to incorrect results, so it's crucial to carefully verify the problem's requirements. Another frequent issue is neglecting edge cases, especially with small arrays. For example, if the input array has fewer than 2 elements, the longest arithmetic subsequence is either the array itself or 0. Failing to handle this properly can lead to runtime errors. Additionally, it's important to account for negative differences. Arithmetic subsequences can involve decreasing patterns, and assuming differences are always positive can cause solutions to be only partially correct. Brute force methods also pose challenges. Though tempting due to their simplicity, they have exponential complexity, which is unmanageable for large arrays, like those of size 10,000 or more. Lastly, incorrect initialization of dynamic programming structures can result in undefined behavior. For instance, forgetting to initialize values for all potential differences can break the logic of your solution, so always double-check your DP setup before implementation. Now, when tackling this problem in an interview, it's important to focus on recognizing patterns. Problems involving sequences, whether subarrays or subsequences, often rely on dynamic programming or hash maps to efficiently track states and avoid redundant calculations. A key skill is breaking down the recurrence relation. In this case, the goal is to understand how the length of an arithmetic subsequence can be extended based on prior results. Another important consideration is space complexity. While hashmap-based DP solutions are efficient in terms of time complexity, achieving n squared, they do require significant memory. For smaller constraints, this trade-off is often acceptable, but in an interview setting, you should be prepared to discuss the implications and potential alternatives. Lastly, clear communication is critical. Interviewers value candidates who can articulate why brute force is suboptimal and how optimizations, such as dynamic programming or hash maps, lead to better results. Explaining your thought process clearly can often be just as important as the solution itself. This problem has connections to several related problems, which can help deepen your understanding of the underlying concepts. For instance, LeetCode 1027, which is the problem we're discussing, focuses on the longest arithmetic subsequence. Similarly, LeetCode 300 deals with the longest increasing subsequence, which has parallels in its use of dynamic programming. LeetCode 413, Arithmetic Slices, is another related challenge, as it also involves identifying arithmetic patterns, but with stricter constraints. Finally, LeetCode 2389, Longest Subsequence with Limited Sum, adds a different twist, focusing on subsequences under a sum constraint. Considering alternative approaches, brute force is a natural starting point for many. It involves trying all possible subsequences and checking if each one is arithmetic. While this is easy to implement, its exponential time complexity, 2 to the power of n, makes it impractical for larger inputs. This trade-off makes brute force suitable only for small-scale problems or as a conceptual exercise. A more efficient approach involves using dynamic programming with hash maps. Here, each index in the array is associated with a hash map that tracks the length of arithmetic subsequences for every possible difference. This allows you to build on prior results efficiently. The time complexity for this approach is n squared, which is significantly better than brute force, but it does come with a space complexity of n squared, due to the hash map storage. While this makes it well suited for large inputs, the memory usage can be a concern, especially for constrained environments. Alternatively, greedy approaches may work for certain variations of the problem. These methods focus on local differences to build subsequences incrementally. However, greedy strategies often lack generality, meaning they may fail to handle edge cases or specific constraints. While they are less memory intensive, you need to carefully evaluate whether they provide correct results for all inputs. Choosing the right approach depends on the problem's requirements and the constraints provided. Great job! We've covered the longest arithmetic subsequence problem using dynamic programming. Remember, mastering these techniques is crucial for tackling sequence-related challenges in coding interviews. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!